In research methodology, research design is a crucial concept that refers to the overall plan or blueprint of a research study.
It is the framework that guides the researcher on how to collect, analyze, and interpret data in order to answer a research question or solve a problem. A well-prepared research design ensures that the research is systematic, organized, and produces reliable and valid results. Research design is not about the actual data collection or analysis, but about planning the structure of the study in advance. It helps the researcher decide what to study, how to study it, and what methods to use. By having a clear research design, the researcher can avoid mistakes, reduce bias, and use resources like time, money, and effort efficiently.
The main purpose of a research design is to ensure that the research answers the research questions accurately and objectively.
It provides guidance on the selection of the research population, the type of data to be collected, the methods of data collection, and the techniques for analyzing the data.
Research design also helps in identifying potential challenges in the study and planning ways to overcome them. In simple words, research design is the blueprint or roadmap of a research study. It provides a structured approach to conduct research in a scientific and organized way. Without a proper research design, research may become unfocused, inconsistent, and may fail to provide meaningful results. Therefore, research design is a critical step in the research process that ensures the study is accurate, reliable, and useful. Significance of research design. In research methodology, a research design is a critical part of any research study. It provides a blueprint or plan for conducting research in a structured and systematic way.
The significance of research design lies in the fact that it ensures the study is organized, reliable, and scientifically valid.
Without a proper research design, research may become random, unclear, and fail to produce meaningful results. 1. Provides a clear framework. A research design gives a clear framework for the research study.
It defines the steps, procedures, and methods to be used in data collection, analysis, and interpretation. This structure helps the researcher stay focused on the research problem and ensures that all aspects of the study are carefully planned.
2. Ensures validity and reliability.
A well-prepared research design ensures that the findings of the study are valid, accurate, and reliable, consistent. It helps select appropriate methods, samples, and data collection techniques that reduce errors and improve the credibility of the results.
3. Saves time and resources. Research design helps researchers plan their study efficiently, avoiding unnecessary steps and mistakes. This saves time, money, and effort and ensures that resources are used effectively. 4. It guides data collection and analysis. A research design clearly explains what data to collect, how to collect it, and how to analyze it. It provides guidance on choosing suitable tools, methods, and statistical techniques, making the research process smooth and organized. 5. Minimizes bias. Research design ensures that the study is conducted in an objective manner, reducing personal bias or influence from external factors. This increases the credibility and scientific validity of the research. 6. Helps in decision-making. A good research design allows researchers to make informed decisions at every stage of the study. It helps in selecting the research approach, methodology, sample, and analysis methods, which leads to better outcomes. 7. Ensures focus on the research problem. Research design keeps the study focused on the research problem. Every step, method, and analysis is aligned with the objectives of the research, which ensures meaningful and relevant results. 8. Facilitates replication. A well-structured research design makes it possible for other researchers to replicate the study under similar conditions. This helps verify results and strengthen scientific knowledge in the field. Conclusion.
In conclusion, the significance of research design lies in its ability to provide structure, ensure validity, save resources, guide data collection and analysis, reduce bias, maintain focus, and allow replication. A well-planned research design is essential for producing accurate, reliable, and meaningful results, making it a crucial step in the research process. It ensures that the research is scientifically sound, organized, and valuable to the field of study.
Types of research design:
exploratory, descriptive, and causal.
In research methodology, a research design is the overall plan or blueprint of a study.
Depending on the objectives and nature of the research problem, different types of research designs are used. The three main types of research design are exploratory, descriptive, and causal, or explanatory. Each type has a specific purpose and approach, and understanding these helps researchers select the right design for their study.
1. Exploratory research design.
Exploratory research is used when the research problem is not clearly defined or is new and little information is available. The main purpose is to explore the problem, generate ideas, and gain insights rather than to provide conclusive answers.
Characteristics of exploratory research design: focuses on gaining basic understanding of a problem. Uses flexible methods like interviews, focus groups, or observation.
Helps in formulating hypotheses or research questions for further study. Not meant to provide definitive conclusions, it is preliminary in nature. Example: a company wants to understand why young customers are not buying its products. Exploratory research may involve interviews or discussions to gather initial insights.
2. Descriptive research design.
Descriptive research is used when the research problem is well defined and the goal is to describe characteristics, behaviors, or patterns of a group, situation, or phenomenon. It does not focus on finding causes but on providing a detailed picture.
Characteristics of descriptive research design: focuses on describing facts and patterns accurately.
Uses methods like surveys, questionnaires, and observations. Data is often quantitative, but qualitative data can also be used.
Helps in understanding trends, frequencies, or relationships among variables.
Example: a study to find the average income, education level, and buying habits of people in a city is descriptive research.
3. Causal, explanatory, research design. Causal research, also called explanatory research, is used to identify cause and effect relationships between variables.
This design is applied when researchers want to determine whether one variable directly affects another.
Characteristics of causal research design: focuses on cause and effect relationships. Uses experiments, field studies, or statistical techniques to test hypotheses. Helps in predicting outcomes based on changes in variables. Requires careful control of external factors to avoid misleading results. Example: a company wants to know if increasing advertising spending will increase sales. A causal study may involve changing ad budgets in different regions and observing the effect on sales. Conclusion:
in summary, the three main types of research design and research methodology are:
exploratory, to explore and gain insights when little is known. Descriptive, to describe characteristics, patterns, or trends of a phenomenon. Causal, to identify cause and effect relationships between variables.
Selecting the right research design is critical for the success of a study, as it ensures that the research objectives are met efficiently, data is collected appropriately, and meaningful conclusions can be drawn.
Components of research design. In research methodology, a research design is a plan or blueprint for conducting a study.
To make research systematic, organized, and reliable, it is important to understand the components of research design. These components guide the researcher in planning, collecting, analyzing, and interpreting data effectively. A clear understanding of these components ensures that the research objectives are achieved efficiently and the results are meaningful.
In research methodology, a research design is a plan or blueprint for conducting a study.
To make research systematic, organized, and reliable, it is important to understand the components of research design. These components guide the researcher in planning, collecting, analyzing, and interpreting data effectively. A clear understanding of these components ensures that the research objectives are achieved efficiently and the results are meaningful. 1. Research problem. The research design starts with a clearly defined research problem. It identifies what the study is about, the questions to be answered, and the purpose of the research. A well-formulated research problem guides the selection of objectives, methods, and the entire research process. Example: a research problem could be, what factors influence consumer preference for organic food? 2. Objectives of research. The objectives define what the researcher wants to achieve through the study. They provide direction and focus for the research and help in selecting the appropriate research methods. Research objectives may be general or specific. Example: to find the most preferred organic food products among urban consumers. 3. Hypotheses. A hypothesis is a tentative statement or prediction about the relationship between variables. Not all research requires hypotheses, but for studies that test relationships or effects, hypotheses provide a basis for testing and analysis. Example: consumers with higher income levels are more likely to prefer organic food. 4. Research methodology. This component defines the overall approach or strategy of the study. It explains whether the research is exploratory, descriptive, or causal. It also includes the methods and techniques for data collection, sampling, and analysis. Example: a descriptive survey using questionnaires to study consumer behavior. 5. Data collection methods. The research design specifies what type of data is needed, primary or secondary, and how to collect it. Primary data is collected directly from respondents through surveys, interviews, or observations. Secondary data comes from existing sources like books, reports, or databases. 6. Sampling design. Sampling design decides who or what will be studied. It includes the target population, sample size, and sampling technique, like random sampling, stratified sampling, or convenience sampling. A good sampling design ensures that the results are representative and reliable. 7. Tools and techniques for analysis. This component explains how the collected data will be analyzed. It includes statistical tools, software, or other methods to interpret the data and draw valid conclusions. Proper analysis ensures that the research findings are accurate and meaningful. 8. Time frame. A research design includes a timeline for the study, specifying when each stage of the research will be conducted. A proper time frame helps in completing the study efficiently and avoids delays. 9. Budget and resources. A well-planned research design also considers the resources required, such as money, manpower, equipment, and materials. Planning the budget ensures that the research is practical and feasible. 10. Reporting and presentation. Finally, the research design specifies how the findings will be reported and presented. It includes the format of the report, tables, charts, graphs, and the structure for presenting the research outcomes clearly. Conclusion. In conclusion, the components of research design include research problem, objectives, hypotheses, research methodology, data collection methods, sampling design, tools and techniques for analysis, timeframe, budget, and reporting. These components provide a structured roadmap for conducting research in a scientific and organized manner. Understanding and planning these components carefully ensures that the research is efficient, reliable, and produces meaningful results. Meaning of variable. In research methodology, a variable is an element, feature, or factor that can change or vary in a study. Variables are the things that researchers observe, measure, or manipulate. Types of variables. In research methodology, variables are the elements, features, or factors that can change or vary in a study. Understanding the types of variables is important because it helps researchers design the study, collect data, and analyze results effectively. Variables can be classified in different ways depending on their role, nature, and measurement. Below is a detailed explanation of the main types of variables. 1. Dependent variable, DV. The dependent variable is the outcome or the variable that the researcher wants to explain or measure. Its value depends on or is influenced by other variables, usually the independent variable. Example, in a study to see how study hours affect exam scores, the exam score is the dependent variable. 2. Independent variable, 4. The independent variable is the factor that is manipulated or considered as a cause to see its effect on the dependent variable. Example, in the same study, the number of study hours is the independent variable because it affects the exam score. 3. Discrete variable. A discrete variable is a variable that can take only specific values and cannot be divided further. Usually, these are counts or categories. Example, number of children in a family, number of books on a shelf. 4. Continuous variable. A continuous variable can take any value within a range and can be measured with precision. Example, height, weight, temperature, or time spent studying. 5. Extraneous variable/control variable. Extraneous variables are variables that are not of interest in the study but can affect the dependent variable if not controlled. Researchers try to control these variables to get accurate results. Example, in a study on study hours and exam scores, factors like sleep, stress, or health may be extraneous variables. 6. Mediating variable. A mediating variable explains how or why an independent variable affects a dependent variable. It acts as a bridge in the relationship. Example, in a study on training programs, 4, and employee productivity, DV, employee motivation could be a mediating variable. 7. Moderating variable. A moderating variable influences the strength or direction of the relationship between the independent and dependent variable. Example, in the same training study, experience level could moderate how training affects productivity. More experienced employees may benefit differently from training. 8. Numerical variable. Numerical variables are measured with numbers and can be either discrete or continuous. They allow mathematical operations like addition, subtraction, or averaging. Example, age, salary, height, or number of hours studied. 9. Categorical variable. Categorical variables are qualitative and represent different groups or categories. They cannot be measured numerically. Example, gender, male/female, type of job, teacher, engineer, doctor, or blood group, A, B, AB, O. Conclusion. In summary, variables in research can be classified based on their role, nature, and measurement. Key types include dependent variables, outcomes measured. Independent variables, factors causing change. Discrete and continuous variables, based on the type of measurement. Extraneous/control variables, need to be controlled. Mediating and moderating variables, explain or influence relationships. Numerical and categorical variables, based on whether data is quantitative or qualitative. Understanding the types of variables is essential for designing research, collecting data, analyzing results, and drawing valid conclusions. Meaning of sample, sampling frame, sampling error, and sample size. In research methodology, sampling is a critical part of data collection. It allows researchers to study a subset of the population instead of the entire population, saving time, money, and effort while still obtaining reliable results. To understand sampling clearly, we need to know the meanings of sample, sampling frame, sampling error, and sample size. 1. Sample. A sample is a small part or subset of the population that is selected for a research study. Instead of studying the entire population, researchers collect data from the sample to make inferences about the whole population. Example: if a researcher wants to study the satisfaction of college students in a city, it is not feasible to survey every student. So, a group of 200 students can be selected as the sample.
2. Sampling frame.
A sampling frame is a list or representation of all the elements in the population from which a sample is drawn. It ensures that every member of the population has a chance of being selected. A clear and complete sampling frame is essential for accurate results. Example: a college's enrollment list can be used as a sampling frame to select students for a survey.
3. Sampling error. Sampling error refers to the difference between the results obtained from the sample and the actual results that would have been obtained from the entire population. It occurs because a sample is only a part of the population. Sampling error can be reduced by increasing the sample size or using proper sampling techniques. Example: if the average marks of 200 students sample is 75%, but the average marks of all 2,000 students population is 77%, the 2% difference is the sampling error. 4. Sample size. Sample size refers to the number of individuals or elements chosen from the population to form the sample. The sample size should be large enough to provide reliable and valid results, but small enough to manage time, cost, and resources effectively. Factors influencing sample size. Population size. Research objectives. Desired level of accuracy and confidence. Available resources. Example: in a survey of 10,000 city residents, selecting 500 people as a sample may provide sufficient accuracy for the research.
Conclusion.
In summary, sample, a smaller subset of the population studied to draw conclusions. Sampling frame, a list of all members of the population from which the sample is drawn. Sampling error, the difference between sample results and actual population results. Sample size, the number of elements included in the sample. Understanding these concepts is essential for designing research, collecting representative data, and ensuring accurate and meaningful results. Characteristics of a good sample. In research methodology, selecting a good sample is very important because the accuracy and reliability of research findings largely depend on it. A good sample represents the population properly and allows researchers to draw valid conclusions. There are several important characteristics that a good sample should have. 1. Representativeness. A good sample should accurately represent the characteristics of the population. This means that the sample should include all relevant features of the population such as age, gender, income, or education. A representative sample ensures that the research findings can be generalized to the entire population. Example: if a city has 60% male and 40% female residents, the sample should reflect a similar proportion. 2. Adequate size. The sample should be large enough to provide reliable and valid results but small enough to manage time, cost, and resources effectively. A sample that is too small may lead to errors and unreliable results, while a very large sample may be expensive and difficult to handle. Example: surveying 50 people from a population of 10,000 may not give accurate results, but 500 people might provide a more reliable picture. 3. Randomness. A good sample should be selected randomly to avoid bias. Random selection ensures that every individual in the population has an equal chance of being included. This increases the validity and reliability of the research results. Example: using a random number generator to select students from a college enrollment list. 4. Homogeneity and heterogeneity. Homogeneity: if the population is similar in nature, a smaller sample can represent the population well. Heterogeneity: if the population is diverse, a larger sample is needed to capture all differences.
Example, studying the preference for a single product in a small neighborhood, homogeneous, versus a large city with different income levels, heterogeneous.
5. Accessibility. The sample should be easily accessible to the researcher. Researchers should be able to collect data efficiently from the selected sample without major difficulties. Example, selecting students from a college that is nearby and has clear records. 6. Avoidance of bias. A good sample should minimize bias in selection. Bias can distort the results and make the findings unreliable. Proper sampling techniques help to ensure fairness and objectivity. Example, not selecting only students from top-performing classes if studying overall student satisfaction. 7. Ability to generalize. The sample should allow the researcher to generalize findings to the population. This is possible only if the sample accurately represents the population and includes all important characteristics. Example, surveying a properly selected group of citizens to understand citywide opinions. Conclusion. In summary, a good sample and research methodology should have the following characteristics. Representative of the population. Adequate size. Random selection. Appropriate homogeneity/heterogeneity. Easily accessible. Free from selection bias. Allow generalization of findings. Understanding and selecting a good sample is crucial for obtaining valid, reliable, and meaningful research results. Types of sampling: probability and non-probability. In research methodology, sampling is the process of selecting a subset of individuals or elements from a population for study. Choosing the right type of sampling is important to ensure accurate, reliable, and representative results. Sampling is generally classified into two main types: probability sampling and non-probability sampling. 1. Probability sampling. In probability sampling, every member of the population has a known and equal chance of being selected. This type of sampling is considered more scientific and ensures that the sample is representative of the population. Probability sampling helps reduce bias and allows researchers to generalize findings from the sample to the entire population. Main types of probability sampling. Simple random sampling. Every individual has an equal chance of selection. Selection can be done using random number tables or computer software. Example, selecting 100 students randomly from a college of 1,000 students. Systematic sampling. Members are selected at regular intervals from a list of the population. Example, selecting every 10th person from an employee list. Stratified sampling. The population is divided into groups, strata, based on a characteristic, and random samples are taken from each group. Example, dividing employees by department and randomly selecting 5 from each department. Cluster sampling. The population is divided into clusters, some clusters are randomly selected, and then all members of those clusters are studied. Example, randomly selecting 3 schools from a district and studying all students in those schools. Advantages: high accuracy and reliability. Representative of the population. Results can be generalized. Disadvantages: more time consuming. Expensive. Requires a complete population list. 2. Non-probability sampling. In non-probability sampling, members are selected based on convenience, judgment, or other criteria, and not every member has a known chance of being selected. This type of sampling is easier and faster but may lead to bias and may not be fully representative of the population. Main types of non-probability sampling. Convenience sampling. Samples are chosen based on ease of access. Example, surveying students who are present in a classroom. Judgmental/purposive sampling. The researcher selects samples based on experience or knowledge about the population. Example, selecting experts to study a specific issue.
Quota sampling: the population is divided into groups, and the researcher fills a specific quota from each group. Example: selecting 10 males and 10 females from each department for a survey. Snowball sampling: existing participants help recruit other participants, often used in studying hard-to-reach populations. Example: studying drug users in a city using referrals. Advantages: quick and inexpensive. Useful when population list is unavailable. Suitable for exploratory studies. Disadvantages: may be biased. Not fully representative. Cannot generalize results confidently. Conclusion: in summary, sampling is essential for effective research. Probability sampling ensures randomness, representativeness, and generalizability, but it is costly and time-consuming. Non-probability sampling is faster, easier, and cheaper, but it may introduce bias and limits the ability to generalize results. Researchers choose the sampling type based on research objectives, available resources, and the population being studied. Sampling and non-sampling errors. In research methodology, errors are differences between the true value of a population and the observed value obtained from the study. Errors are common in research, and understanding them helps researchers interpret results correctly and take steps to reduce them. Broadly, errors in research are classified into sampling errors and non-sampling errors. 1. Sampling error. Sampling error occurs when the sample chosen does not perfectly represent the population. Since a sample is only a subset of the population, some difference between the sample result and the actual population value is natural. Characteristics of sampling error. It is unavoidable, but it can be minimized by increasing sample size or using proper sampling techniques. It arises due to chance variation in selecting the sample. It is quantifiable, meaning researchers can estimate its size statistically. Example: if the average income of 500 people in a city sample is 45,000 Indian rupees, but the actual average income of all 5,000 people population is 46,000 Indian rupees, the 1,000 Indian rupees difference is the sampling error. Causes of sampling error. Small sample size. Poor sampling method. Random variation. 2. Non-sampling error. Non-sampling errors are errors not related to sampling. They can occur even if the entire population is studied, and are usually caused by mistakes in data collection, processing, or measurement. Non-sampling errors are often more serious than sampling errors because they can introduce bias. Characteristics of non-sampling error. Can occur in any research study, not only in samples. Often difficult to measure or quantify. Can be systematic, meaning they affect results consistently and lead to bias. Types of non-sampling errors. Measurement error, incorrect answers due to poorly designed questions or faulty instruments. Example: respondents misunderstanding survey questions. Data processing error, mistakes in recording, coding, or analyzing data. Example: entering wrong values in spreadsheets. Non-response error, when some selected respondents do not participate, affecting representativeness. Example: people refusing to answer a survey about income. Interviewer error, bias introduced by the interviewer's behavior or attitude. Example: in a survey, if respondents lie about their income or the survey form is filled incorrectly, the error is non-sampling error. 3. The differences between sampling and non-sampling errors. Feature. Sampling error. Non-sampling error. Cause. Due to using a sample instead of the full population. Due to mistakes in data collection, processing, or measurement. Occurrence. Happens only in sampling studies. Can happen in both sample and census studies. Controllability. can be reduced by increasing sample size or proper sampling. More difficult to control, requires careful design and supervision.
Nature. Usually random. Can be systematic, bias. Conclusion. In summary, sampling errors are natural differences that occur because a sample may not perfectly represent the population. They can be estimated and reduced. Non-sampling errors are mistakes or biases that occur during data collection, recording, or analysis.
They can be more serious and may distort research results. Understanding both types of errors is essential for designing research, improving accuracy, and interpreting results correctly.
Hypotheses formulation, meaning. In research methodology, a hypothesis is a clear and testable statement or prediction about the relationship between two or more variables. It is an educated guess based on existing knowledge, theory, or observations, which the researcher tries to test through research. Formulating a hypothesis is an important step in the research process because it gives direction and focus to the study. Meaning of hypothesis formulation. Hypothesis formulation means the process of creating a specific, clear, and testable statement that explains what the researcher expects to find in a study. It acts as a guide for designing research, collecting data, and analyzing results. A well-formulated hypothesis allows the researcher to verify or refute the predicted relationship between variables using evidence. Example: if a researcher wants to study the effect of study hours on student performance, a hypothesis could be: students who study more hours will score higher marks than students who study fewer hours. This statement is clear, specific, and testable. Key points about hypothesis formulation. Prediction or statement. A hypothesis is always a predictive statement about what is expected to happen in the study. Relationship between variables. It shows the expected relationship between two or more variables, usually an independent variable and a dependent variable. Testable. A hypothesis must be testable through observation, experimentation, or data analysis. Based on theory or knowledge, it is usually formed based on existing knowledge, prior research, or theoretical understanding. Provides direction. Hypotheses give focus and direction to research, helping the researcher know what data to collect and how to analyze it. Importance of hypothesis formulation. Helps in clarifying the research problem. Provides a basis for designing the study and choosing research methods. Helps in data analysis, as researchers know what relationships to test. Allows researchers to draw conclusions based on evidence rather than guesswork. Makes research organized, systematic, and scientific. Conclusion. In simple words, hypothesis formulation is the process of creating a clear, specific, and testable statement about what a researcher expects to find in a study. It is a vital step in research methodology because it guides the entire research process, helps in testing relationships between variables, and ensures that research is scientific, focused, and meaningful. Characteristics of hypothesis. In research methodology, a hypothesis is a clear, testable statement or prediction about the relationship between two or more variables. A well-formulated hypothesis has certain important characteristics that make it useful, reliable, and scientific. Understanding these characteristics helps researchers form proper hypotheses and conduct meaningful research. 1. Clear and specific. Specific. A hypothesis must be clear, precise, and easily understandable. It should specify the variables being studied and the expected relationship between them. A vague or unclear hypothesis can create confusion and make research difficult. Example: students who study more hours score higher marks than students who study fewer hours. This is clear and specifies the variables, study hours and scores. 2. Testable/verifiable. A hypothesis should be testable through observation, experimentation, or data analysis. Researchers must be able to collect evidence to either support or reject it. Example: the relationship between exercise and weight loss can be tested by collecting data from participants. 3. Based on theory or knowledge. A good hypothesis is grounded in existing knowledge, theory, or prior research. It should not be a random guess but should reflect logical reasoning based on facts and observations. Example: a hypothesis about nutrition and health can be based on previous scientific studies. 4. Predictive in nature. A hypothesis always predicts an outcome or relationship between variables. It tells the researcher what to expect in the study. Example: higher temperature increases the growth rate of plants. 5. Simple and concise. A hypothesis should be simple and easy to understand, avoiding unnecessary complexity. Simple hypotheses are easier to test and interpret. 6. Logical. A hypothesis must be logical and reasonable. The predicted relationship should make sense based on known facts and existing knowledge. Example: expecting sunlight to affect plant growth is logical, but expecting plants to grow without water is illogical. 7. Measurable/operational. The variables in a hypothesis should be measurable so that data can be collected and analyzed. Operational definitions of variables help in testing the hypothesis accurately. Example: study hours can be measured in hours per day, and student performance can be measured in marks. 8. Statement of relationship. A hypothesis usually describes a relationship between independent and dependent variables. It may suggest that one variable affects another or that variables are correlated. Conclusion. In summary, the key characteristics of a good hypothesis are: clear and specific, testable/verifiable, based on theory or prior knowledge, predictive in nature, simple and concise, logical, measurable/operational, describes a relationship between variables. A well-formulated hypothesis guides research design, data collection, and analysis, ensuring that the study is scientific, focused, and meaningful. Basic concepts relating to hypothesis testing. In research methodology, hypothesis testing is an important process used to determine whether a hypothesis about a population is supported by the sample data. It is a systematic way of making decisions about a statement, hypothesis, based on evidence from data. Understanding the basic concepts of hypothesis testing is essential for conducting accurate and reliable research. 1. Hypothesis. A hypothesis is a clear, testable statement or prediction about the relationship between variables. Hypothesis testing evaluates whether the evidence supports or rejects the hypothesis. Example: students who study more hours score higher marks. 2. Null hypothesis, H. The null hypothesis is a statement that there is no effect or no relationship between variables. It represents the default position or status quo. Example: study hours have no effect on student marks. The purpose of hypothesis testing is often to test whether the null hypothesis can be rejected based on data. 3. Alternative hypothesis, H or HA. The alternative hypothesis is a statement that there is an effect or a relationship between variables. It is what the researcher aims to support. Example: students who study more hours score higher marks. If evidence from the data is strong, the null hypothesis is rejected in favor of the alternative hypothesis. 4. Type of errors. When testing hypotheses, two types of errors may occur. Type 1 error, alpha, rejecting the null hypothesis when it is actually true. Example: concluding that study hours affect marks when in reality they do not. Type 2 error, beta, failing to reject the null hypothesis when it is actually false. Example, concluding that study hours have no effect when they actually do.
5. Significance level, alpha.
The significance level is the probability of making a type 1 error.
It is often set at 0.05 or 5%, meaning there is a 5% chance of wrongly rejecting the null hypothesis.
6. Test statistic. A test statistic is a numerical value calculated from sample data that is used to decide whether to reject the null hypothesis. Common test statistics include t-test, z-test, chi-square test, and ANOVA. 7. P-value.
The p-value measures the probability of obtaining results as extreme as or more extreme than the observed results, assuming the null hypothesis is true.
If p-value less than or equal to alpha, reject H, null hypothesis. If p-value alpha, do not reject H. 8. Decision rule.
The decision rule is based on comparing the test statistic or p-value with the critical value/significance level. It determines whether the null hypothesis should be rejected or not rejected.
9. One-tailed and two-tailed tests. One-tailed test tests for an effect in one direction. Example, study hours increase marks. Two-tailed test tests for an effect in both directions. Example, study hours affect marks, either increase or decrease. 10. Importance of hypothesis testing.
Helps to make informed decisions based on data. Distinguishes between real effects and random variations.
Ensures research conclusions are scientific, reliable, and evidence-based.
Guides policy decisions, academic research, and practical applications.
Conclusion.
In simple words, hypothesis testing is a structured method for evaluating whether a statement about a population is supported by sample data. It involves defining null and alternative hypotheses, selecting significance level, calculating test statistics, comparing results, and making a decision. Understanding these concepts ensures that research is systematic, logical, and produces trustworthy results.
Types of hypothesis testing. In research methodology, hypothesis testing is a process used to determine whether a hypothesis about a population is supported by sample data. There are different types of hypothesis testing, depending on the research objective, type of data, and direction of the test. Understanding these types helps researchers choose the appropriate method for analyzing their data. 1. One-tailed, directional, test. A one-tailed test is used when the researcher wants to test the hypothesis in one specific direction. It predicts that the effect or relationship will occur in a particular way. Example. Students who study more hours will score higher marks. Here, the prediction is that marks will increase, not decrease. Use. One-tailed tests are useful when the research has a clear expectation of the effect. 2. Two-tailed, non-directional, test. A two-tailed test is used when the researcher is testing whether there is a relationship or effect in either direction. It does not assume whether the effect will increase or decrease, it only checks if there is a difference. Example. Study hours affect student marks. This tests whether study hours increase or decrease marks, without specifying the direction. Use. Two-tailed tests are more conservative and widely used when the direction of the effect is not certain. 3. Parametric tests. Parametric tests are used when the data follows a known distribution, usually normal distribution. These tests assume that certain conditions, like equal variance and interval or ratio data, are met. Common parametric tests. T-test compares means of two groups. ANOVA, analysis of variance, compares means of three or more groups. Z-test compares sample mean with population mean. Use. Parametric tests are preferred when data is continuous, normally distributed, and meets assumptions. 4. Non-parametric tests. Non-parametric tests are used when the data does not meet the assumptions required for parametric tests, such as normal distribution or interval data. They are more flexible and can be applied to ordinal or nominal data. Common non-parametric tests. Chi-square test tests relationship between categorical variables. Mann-Whitney U test compares two independent groups. Wilcoxon signed rank test compares two related groups. Use non-parametric tests are useful when data is categorical, skewed, or small in size. 5. One sample and two sample tests. One sample test compares the sample mean or proportion with a known population value. Example, testing if the average study hours of a class differ from 5 hours. Two sample test compares two independent samples to see if they differ. Example, comparing test scores of students in two different schools. 6. Paired, dependent, and independent tests. Paired/dependent test compares two related observations, like before and after measurements. Example, test scores of students before and after a training program. Independent test compares two separate groups. Example, comparing male and female students' performance. Conclusion. In simple words, hypothesis testing types depend on the direction of prediction, the nature of data, and the relationship between samples. The main types include one-tailed versus two-tailed tests, directional versus non-directional, parametric versus non-parametric tests, data assumptions, one sample versus two sample tests, number of samples, paired versus independent tests, related versus independent data. Choosing the correct type of hypothesis testing ensures that the research results are accurate, reliable, and meaningful, allowing researchers to draw scientific conclusions.